The chemistry of the ozone and the chemistry of the atmosphere is what we call radical chemistry. A radical is a chemical species that has one single electron, which is unpaired. It has one electron in its outer shell, which is not paired, is not making a bond. They are very reactive species. When you have a species, a chemical species which is a neutral molecule and has just an unpaired electron, we call that a free radical. How do you form free radicals? Well, they are formed by the homolytic breakage of a chemical bond. Typically, in typical conditions, a bond does not, a bond between two atoms, a bond made by two electrons between two atoms, does not break evenly. Typically, one of the atoms will take away the electrons, but when you have a homolytic fragmentation, it means the bond breaks down the middle, and you form each of the species, A and B, the two elements that were making part of the bond, but separately, and each of them walks away with one of the electrons from that bond. How can you make radicals? Well, one way of making radicals is temperature. At sufficient temperature, any molecule, any chemical compound will dissociate into radicals. And another way, and the way it happens in the atmosphere, is by absorption of UV radiation of the right wavelength to break the bond. So this is an example of a compound X2, two atoms bonded, sharing two electrons in a bond, and when the radiation of the right wavelength hits that bond, the bond splits down the middle, and the two elements, each of them walks away with one of the electrons from the bond. This is the generic way we have to express radiation. H is Planck's constant, and nu is wavelength. So when the right wavelength to break the bond for the molecule of chlorine comes, the bond splits down the middle, and each of the chlorine atoms walks out with one electron, and they become chlorine radical. And in this case, for example, this is a peroxide group, the single bond between the two oxygens, and again, when the right frequency, the right wavelength of UV light hits the bond, it gets absorbed, the bond breaks between the two oxygens, and each of the oxygens walks away with one of the electrons from the bond. And it's the wavelength, the wavelength of that radiation that will determine which bonds will absorb the radiation, which bonds will be broken. Atmospheric chemistry is full of photochemical reactions. What are photochemical reactions? So what is photochemistry? Well, we are looking at how the absorption of photons of light into molecules, atoms, molecules, ions, help them reach what they call an excited state, a high energy state, and that will enhance a series of reaction of those molecules, of those atoms. And that's what photochemistry is. The first step in any photochemical process is the absorption of electromagnetic radiation, the solar radiation, of a particular wavelength appropriate for that particular element. So for example, here you have the example of an atom of sodium that will have a particular electronic configuration with electrons in the different orbitals that make up the atom of sodium. And we are looking specifically at this electron which is in the outer shell. When the right wavelength hits the atom of sodium, that electron is able of absorbing that radiation and reach what we call an excited state. The electron is in a higher energy orbital. It's an unstable state, but the amount of energy communicated by the photon of that wavelength has allowed that electron to reach a higher energy orbital. And then that's unstable. It's not an stable state, so it will quickly revert back to its original orbital, trying to reach a more stable state, and the radiation will be emitted. We call that excited state, we call that high energy state the excited state, and we denotate it with this asterisk. When you add an asterisk to a chemical structure, it means that particular compound, a fragment of a molecule or a complete molecule or an ion, has absorbed a certain amount of solar radiation with a particular frequency that has allowed electrons to reach higher orbitals. Once a species has reached an excited state, it can evolve in several ways. Sometimes it will reach a lower energy state by just releasing back the energy that has absorbed, and then nothing happens. But other times it will be able to produce different products, do something more than just absorb a photon of light and then expel it again. For example, a molecule that has reached an excited state could dissociate, breaking the bond, the homolytic bond, a homolytic breakage between the two atoms, and produce two radicals. So you have here, for example, how the formation of two chlorine radicals, or the formation of the nitrogen monoxide radical and oxygen radical by splitting those two molecules. Other times it might find another chemical and produce a reaction. So you end up not with just splitting the bond, as in a dissociation process, but just making a different compound. This is, for example, when an atom of oxygen in an excited state finds a molecule of water, and you can create the hydroxyl radical. And another pathway that molecule in that excited state can take is what we call photoionization, which is it liberates an electron and it becomes positively charged, a radical with a positive charge. And here we've got the example of how nitrogen monoxide, when with the right electromagnetic radiation, the right solar radiation, with the right wavelength, will achieve an excited state, and it immediately will evolve, because it's an unstable state, immediately will evolve to produce the nitrogen monoxide cation and liberate an electron. So as you can see, there are several pathways that our excited molecule can follow, and that's what makes atmospheric chemistry such a rich chemistry, and to a certain extent such a complicated chemistry.